Yeah, it's my great pleasure to share with you guys some of our researches about nano-structured composite materials for environmental benign antimicrobial technologies. The problem is, as we know, that antimicrobial resistance actually is one of the major threats to our public health. And showing this part of a chart, and you may seen this before, the deaths related to antimicrobial resistance could be reached 10 million in 2050s. So this, we know that the bacterial cells, they can develop different type of approach for this resistance, such as this drug reflex pump, and they reduce the permeability of the cell membrane. They can have the enzyme to degrade drugs, or they can alternate the drug targeted by gene mutation. So here in our group, we try to develop an antimicrobial technology with a low potential of resistance development, and we try to mitigate these transmissions by developing a self-disinfecting surface. This is the outline of my presentation. It will have two parts. The first part is a nano-structured self-disinfecting surface, and the second part is a Redox reactive oxygen species releasing metal composites. For the nano-structured surface, cells on the surface, they have a different behavior or performance. Typically, for the general biomaterial surface, the cells can stay on the surface, but for some surface, actually they have a repairing effect. The cells will be repaired from the surface. And on the other hand, there can also be an adhesive surface will attract the cells on the surface. And in the nature, we know that when there's a kind of a nanostructure on the surface, when this the parameter of nanostructure is above 10 microns, then the cells will very happily and healthily on the surface. They can stretch by using this type of the structures. But if the parameter of nanostructure is between 1 micron to 10 micron, then typically this type of surface will repair the cells. For example, this shark skin is a well-known one that will repair all the microbes or other features. But if the surface nanostructure, the parameter further go down to sub-micron scale, then this kind of nanostructure will kill the attached cells, and this we consider a physical rupture mechanism. There's no toxic chemical releasing. We can consider non-toxic killing behavior or mechanism. They generally have a broad spectrum because they are not target the specific target. It's just that penetrate the cell membrane, cause the lysis, and they have much lower opportunity to create superbugs. So based on these kind of properties, so we are interested on develop this type of nanostructured surface to create a self-disinfection surface. So when we look at this, the Nature or some other people reported Nanopattern surface, most of them, they are use this top-down approach. They start from bulky materials and then go by etching or more replication method to develop this nanostructure. And showing here some example. This is the scattering, it's a nature one, and this is PMMA, titanium surface, or black silicon. These all created by this etching or more replication method. Is a top-down method. So this type of method is quite complex, and it's lack of practicality and scalability. And here for us, and we have developed this bottom-up approach. Basically, it's start from atom or small molecules. They glue this kind of nanostructure on different surface as shown here. So this is a very simple and scalable synthesis approach. We can easily develop prototypes or products for real application. As shown here is the first example. We call this Disinfection ZIF Coatings. The ZIF represent zeolite imidazolide frameworks, ZIF. And firstly, we can glue this nanostructure on different surfaces. We can control the parameters of structure by just simply adjust the synthesis conditions, and as shown here. And we can glue this nanostructure on various different surfaces, from the very hydrophobic one, Teflon, to hydrophilic, like a wood and filter paper. And it can be easily glued on a hard and flat surface, and it can also be glued on a flexible surface like cotton fiber. This is how it looks like. The structure looks like, we call this a nano sword or nano daggers, and it has sharp tips. And actually, it has a positive charge on the surface because we use a lot of imidazole as a ligand for these materials. And their hair is typically about 1 micron. The tip distance is about 200 to 1,000 nanometers. So we can glue or coat this structure on various surfaces. And here is the killing mechanism for this type of structures. Basically, they have these sharp nanostructures, and they have positive charge. They attract the negative charged cell membrane cells onto the surface, and then the sharp tips will penetrate the cell membrane and cause cell lysis and cause the cell death. Showing here is the SEM image. You can see this is the C. albicans cells. Actually, it really penetrates by these tips of the nano dagger. And showing here is some killing efficacy of ZIF nano-arrays. This one is against the E. coli, and you can see we have 2 different types of coatings. The red one is a ZIF A coating on PMMA. This is the coating without nanostructure. It's a smooth layer. But the blue one is a ZIF L coating with this. We just seen this nanostructure, nano-array structure. This ZIF A and ZIF L, they have the same chemical component, but you can see here, the blue one has excellent killing properties, but red one basically is no killing. And similarly for the SA, also the C. albicans, they all demonstrate good killing, because we also try to challenge the coating surface repeatedly at different time, and they all give very good results. And also this ZIF coating on different substrates like glass, silicone, or filter papers all give very good bacterial killing properties. Showing here is one application examples. So we know that for the wound healing, there's a commercial product. They use a silver as this antimicrobial contact layer. But here we take a cotton gauze. We just coat with this ZIF nanostructure on the cotton fiber, and showing here the SEM. And then we use this for covering the wound, develop this wound model, and then compare with the commercial one. And actually, you can see from here, after like day 11, the wound healing performance for our materials is at least comparable with commercial one. And from this bacterial counting, you can see our materials even better, has a much less bacteria as compared to the commercial one. And yet our materials is much safe and biocompatible as compared to this commercial. And other than this ZIF, we also try to looking for more durable and stronger these nanostructured materials. And showing here is the zinc oxide nanopattern. We glue this zinc oxide nanopatterns on different type of surface, on glass, on titanium, and also on the zinc foils and some others. When we do this antimicrobial evaluation by use this GISZ 2801 measure, and we found that these nanopillars on surface like glass, titanium, selenium, PMMA, silicon, it has no killing. But on the zinc and zinc plated iron have excellent killing. And then we further look at the surface, look at the attached cells. Actually, all the attached cells are killed, regardless on what kind of a substrate. But only on the zinc and zinc modified iron, they have this killing for the GIS measure. Actually, it is because the GIS measure, and then it is both attached and dispatched cells. So for typical nanostructure, they only kill attached cells. But for zinc oxide on zinc, actually they can kill both attached and dispatched cells. For the mechanism, as I shown here, So this zinc oxide nanoneedles on zinc, they have multiple mechanisms. Firstly, they can penetrate the cell membrane by this nanostructure. At the same time, they can also through this electron donation to zinc oxide and then reduce oxygens to superoxide radical. So this radical will kill the remote bacterial cells. This has been proved for this superoxide measurement, and you can see zinc oxide on zinc actually gives much higher superoxides as compared to others like zinc oxide on glass, on titanium, or zinc cells. And we also did this ROS scavenger experiment showing that when added in the scavenger, showing here, the active, the antimicrobial protein is disappeared, and further prove that this ROS mechanism. For the more wide applications, we did this dermal toxicity of zinc oxide nano-array. Basically, we caught this metal shelf with nano-structure, as shown here. This is a coated one, this is a non-coated one, and this is the SEM of the surface. And then we put the mice on this metal shelf for 4 weeks. Actually, we did not see any skin issues for this control and coated and uncoated surface. From the histological analysis of main organs, there's no changes. And also from blood biochemistry analysis of mice exposed to these 3 surfaces, also confirmed no abnormals. So this means this nano-array coated surface is biocompatible. And for the real application, one of the questions is the durability, because when you expose this surface for different application, different real situations, what will happen? So here we did this durability test, and showing all the SEM here. From A is the control, B is the dry brushing up to 1,000 times, C is the wet brushing 10,000 times, and D is the protect in water for 6 hours, and E is exposed to Dettol, one of the most commonly used the disinfectant agents, and F is exposed to bleach, and G is a low pH, pH 4, H is pH 6, and I is pH 12. And from the results shown here, other than the G, the low pH, or other case, the nano-array structure is basically retained. And even for the G, including G, all this surface after this durability test, their antimicrobial properties is well retained, still demonstrate very good antimicrobial properties. And we're also looking for the other nanostructured materials by using the more environment benign one. For example, showing here is iron-based nanostructures, and we grew this iron oxide on different substrates such as glass or metals. And showing here, they also demonstrate good antimicrobial properties. And here is the E. coli on the surface, all cured. And we can also reformate this nanostructure in we call this ocean format, the particle format with the nanostructure. And this can offer more general applications such as for coating. And again, we can see that with this nanostructure demonstrate good killing, but with our nanostructure, you just green this wound chain particle to a random materials, then the antimicrobial property also gone. So this is for E. coli, this is for aureus. Other than that, we're also looking for more biocompatible materials. And showing here is we call this vertical aligned laid double hydroxide, because this type of material have been widely used for the in-plane. So it's a well-known biocompatible materials. And here we grew this vertical aligned structure on different surface. And this is a synthesized structure, and this is after calcination. And actually, you can see after calcination, the structure becomes much thin and sharper. And another important point is becomes more hydrophilic. And when we look at the antimicrobial properties, and showing here against the E. coli, you can see for this synthesized one actually did not show much healing, but for the after calcination, it has great antimicrobial properties. And then we glue this structure on the titanium. It's a widely used implant materials. And you can see after calcination here. And we make this titanium disc. And this is a non-coated and this is a coated one. And then put it in a vials to do this in vivo experiment. After 6 months, they did not see much difference between materials from the before implant. And also from the historical analysis of tissues, we did not see any difference. And it means this the LDH materials glue on the titanium has a very good antimicrobial property and also the biocompatibility. And for the nanostructured space, this is the last one. It's a copper space. And we are looking for this fast killing and also antivirus properties. Because we know that virus size is much, much smaller than bacteria. So typically this kind of nanostructure won't cure, cannot cure the virus. But here, when we develop this, the copper-based like nanoswirl or nanoforms, actually it demonstrates good antiviral properties. And showing here is some result. So firstly, we have this copper soft balls, and we treat that for this nanostructure, and then we put it in this air chambers for airflow to pass through these chambers. And we place this device in an enclosed room, and then we let the airflow go through these chambers. And you can see after several cycles, the bacterial content in the room is keep dropping. It really has played the role as an antimicrobial filter. And showing here is the antivirus test. We take this MS2, the bacteriophage, and also we take this the MHV as a surrogate for the SARS-CoV-2 virus. And these materials demonstrate very good fast killing properties against these two viruses. So for the killing mechanism as shown here, with these nanostructures, and one side, it can kill the bacteria by using this nanostructure. Another side with a much, much higher surface area, they can have a fast releasing of copper cations into the surroundings. And these copper cations can kill the bacteria and also the virus. So that's why these materials have fast killing and antibacterial and also antivirus properties. So with that, I will move on to my second topic, is reactive oxygen species releasing metal composites. So we know that some of the semiconductors has photoactive properties such as titanium oxide or zinc oxide. Under UV irradiation, they can release ROS, reactive oxygen species. And this property is further extended to the visible light by changing their component and structures. And here we develop this, we call a kosher nanostructure materials. They can convert oxygen and water into different type of ROS. And this conversion is basically by electron donate from zinc to zinc oxide, core and shear. And then they can reduce oxygen to silver oxide and further convert to hydrogen peroxide or others. So with this design, the materials is basically synthesized from the natural component. They are non-toxic. They do not have a toxic chemical releasing. They have a long-term activity, and they can work in dark. Do not need the light and all conditions. And from the safety profile, they have no hemolysis issue. There are no gene toxic and no skin irritation. And the oral toxicity is also considering safe and no safe materials. It's more than 2,000 milligrams per kg. And showing here is some properties. So it has a very good antivirus properties. And again, this is the MHV. We coat these materials on airplane seat cover. And you can see, even after 30,000 times of the washing, the seat cover still have excellent antiviral properties. And here is the ROS releasing properties. So for our materials, this is marked as a GA. They release much higher ROS even in dark compared to the zinc oxide and UV. And also for the shelf life, this material is very stable. After 24 months, it still have the same properties as compared to the newer one. And we can also manipulate or change the component or structure of this co-shear path and to achieve different functions. And showing here, there's a different type of materials, co-shear materials. And some of them, they can release more superoxide and hydrogen peroxide, as shown here. But some others can release more singlet oxygen and hydrogen peroxide radicals. So by doing this, we can really choose different materials for different applications. And showing here is some application examples. The first one, so we can use these powder materials as ingredients to form spray coating formulations. And then we can use this to coat different surface. And for example, we can use these compressed air spray tools to do this formulation, to do this coating on metal surface, on plastic, on textile, or on glass, on wood. Basically, all kinds of surface we can do this spray coating. And after the coating, the materials really demonstrate excellent properties, antimicrobial properties. And showing here, you can see as coated one, they can cure both the MS2 and the MHV. And after 30,000 times of durability test, as a abrasion test, the materials still have very good antivirus properties. And the same materials we can also use as antimicrobial ingredients for paints and for different paints. For example, we can just use for the wall paints and for your office. And these materials can create a bacteria-free surface. And interestingly, this material actually can also degrade the formaldehyde to provide a clean environment for you, especially as in the room. And they can also be used as the antifouling paints. And showing here is one example when the paints incorporate with some of our materials, and then there's a quite the clean and the no fouling stuff. But without adding our materials, you can see this is a really a lot of materials is attached on the surface. And another example is we can directly load our materials on these textiles by the washing machine. And after loading this, the material, the textile has a long-term antimicrobial activities. And even after 40 times of water challenge and washing cycles, the materials still have excellent antimicrobial properties. So in addition, our materials can also be used to make antimicrobial plastics. Then basically you just use this as an ingredient, and during the molding process, you add on the plastics, then the plastic will have these properties. For example, for this ABS, the polypropylene, and also even for this fiber, PLA fiber. Then after incorporate of our materials, then all these plastics demonstrate good antimicrobial properties. And we also try to compare with the one of the most commonly used in the market is the silver-based antimicrobial ingredients. And you can see here for PVC, and 0.5% of our materials and demonstrate excellent antimicrobial properties. But for the PVC with 2% of silver-based materials, and their efficacy is much less or worse than our materials. And similarly for the rubber-based plastics, and our materials also demonstrate much better performance as compared to the silver-based one. Other than these applications, and for all our materials I present here, they have a really very general or broad spectrum of antimicrobial properties. And here I just show you, we test our materials like this co-shear particles, also nanopillars, or the copper-based nanoblader or nanotubers against clinical isolations and drug-resistant species. And as shown here, you can see all of our materials against this type of species that demonstrate really excellent antimicrobial properties. So with that, I will end my presentation, and I would really thank all of my group members for their hard working and collaborators from different organizations, universities, and also the institutions, and also the industry collaborators. Actually, these two companies, the Extra Nanotech and Polymer Green Tech, they are the spin-off companies from our institutes, and they are licensed our technology and to form company, and now there's a product already in market. And we are also working on with other companies for various applications. The funding is from our NRF, CRT, ICB, IBB, Enterprise, BMRC, and A-Star. Thanks. I would like to answer any questions.